In this video, we are going to talk about Gaussian elimination method and its close relation to the matrices and row operations. Let's consider an example of a system with three linear equations and three unknowns x, y, and z. The basic idea is very simple. That is, we are going to use the first equation to somehow clean off the x's in the later equations, and then repeat the process for the y unknown. Before we do that, let me go ahead and switch equation 1 and equation 3. This is for simplicity purpose. As you can notice, there is only one x on equation 3, so that will help us simplify our computations later on. Now that we have the single x on the top, and we are going to use it to eliminate the 3x and the 2x below. In order to do so, we first multiply the whole equation 1 with negative 3 and add that directly to equation 2. If we do that correctly, we should be able to get negative 5y plus z equals negative 3. And we are going to mark and note by writing that equation 2 an arrow, which means it has become equation 2 itself plus negative 3 times equation 1. Similarly, we are going to multiply equation 1 with negative 2 and add that to equation 3. And as a result, we are going to have negative 2y plus z equals 0. Now we have successfully eliminated all the x's below the first equation. The next step is to repeat the whole process for the unknown y on a smaller scale. Because neither 5 nor 2 is a multiple of the other, to help us simplify our later computations, we first multiply the whole equation 3 by negative 5. If we do that correctly, we should be able to get 10y minus 5z equals to 0 as below. Next, we'll try to eliminate the y below. In order to do so, we multiply equation 2 by 2 and add that directly to equation 3. We should be able to get negative 3z equals negative 6. Now we are going to find the solution for the system of linear equations by tracing back from below. Starting from the easiest equation from below, negative 3z equals negative 6, we can easily find z equals 2. After we know z equals 2, we are going to replace that back to equation 2 and we are going to find y. After we know both y and z, we are going to replace them back to equation 1 and we are going to find x. So the solution for the system of linear equation is the column vector negative 3, 1, and 2. And because we are tracing back from below, this is called the backward solution. Let's look at what we have done so far. We have used Gaussian elimination method to successfully solve the system of linear equations. But do you notice that there was something that we had to write over time again and again? For example, the x's, the y's, the z's, the plus sign, the equal signs, and the curly brackets. To save us time, why don't we just erase them all and keep in mind that they are there in case we need to trace back. For example, the first column is always associated with the x variable. The second column is associated with the y variable. The third column is associated with the z variable. And the last column is reserved for the coefficients on the right-hand side. Before we do that, let me go ahead and put the number 1s in front of the single axis, y's, and z. The purpose is to prevent us from misthinking that there is nothing there after we erase them all. Also, where we don't see any x or y are where we have 0x and 0y. Now we are ready to erase all the unnecessary things. And what we end up having is something look like matrices. The first matrix is actually called the augmented coefficients matrix for the linear system. In addition, we draw a line to help us remember that there is a major difference between the coefficients in the last column and the others. Also, what we did on the equations turned out to be what we would do on the rows. And these are called the row operations. If you pay attention, you would see that the last matrix is actually the staircase matrix. In other words, it is in echelon form. Once you have the echelon form, you can start using the back solution method to get x, y, and z. For example, we'll start with the last row, which is -3 and -6. -3 is on the third column and it is associated with the z variable. So we in fact have -3 times z equals to -6. That leads to z equals to 2, and from there we can easily get y and x. However, if we try to reduce the echelon form to the row reduced echelon form, then you will see some magic. In order to obtain the row reduced echelon form, we first need to turn the pivot entries -5 and -3 into 1, and also turn all the entries above them into zeros. In order to do so, first we divide row 3 by -3 as an attempt to make 1. And now we use the number 1 to zero out the other entries above it. To do so, we subtract row 2 by row 3 and subtract row 1 by row 3 as well. Next, we divide row 2 by -5 to make 1. Again, we use the number 1 to zero out the entries above it. In this case, we subtract row 1 by 2 times row 2. And congratulations, you have obtained the row reduced echelon form for the augmented matrix of the original linear system. Do you notice that the column on the right is exactly the solution for the system? Why? Think about it.